Hello, hi. Myself Manohar Ghanta, along with my team members Aasslesh Kola and Jagadeesh Kanumilli, are here to explain about Hadoop for cloud computing. Coming to the introduction, let us first know about the big data and how it is connected with the Hadoop and some history about the Hadoop. One of the largest technological challenges in software systems research today is to provide mechanism for storage, manipulation, and information retrieval on large amounts of data. Web services and social media produce together an impressive amount of data reaching the scale of petabytes daily. Example for the Facebook. These data may contain valuable information which sometimes is not properly explored by the existing systems. Most of this data is stored in a non-structural manner using different languages and formats which in many cases are incompatible. The image you are looking at is the image of a Facebook page. The Facebook page consists of the videos, photos, text, and different kinds of data. The Facebook, which initially used the relational database management system to store its data, now, due to the increase of the large amount of information generated on the daily basis, the use of such infrastructure became impractical because the number of users for the Facebook has been increased day by day, and the uploads of the photos and the videos have been increasing day by day. All the people of different kind are being uploading different kinds of photos and everything. The data has been increasing in size, like from the MBs, GBs to TBs, now in PBs, especially because most of the data is unstructured, consists of logs, posts, photos, and pictures. One of the Facebook's largest cluster holds more than 100 PB of data, processing more than 60,000 queries a day. This is not a small amount of data. Its processing is very large. So if we leave now like this, the data is going to be increased day by day, day by day, day by day, and it's going to be like we cannot store anywhere. Coming to taking an example, if we take our as an example, previously in 1990s, the data is we used to keep in our systems, it used to be like 1 GB the max. Okay, now in our laptops, the hard disk size is gonna be like 500 GB 1 TB. Okay, we are using the external hard disk to store our data, but if we go on leave like that, by 2050 we're gonna be storing the hard disk like the CDs we used to keep before. The number of hard disks increase and the number of photos increase. We don't want to lose any data of ours. So now it's better to take any step to reduce the size and easily save our data without wasting any hard disks. The map reducing programming, now highly used in the context of big data, is not new. One of the first uses of this was on the Lisp programming language. It relies basically on two functions, map and reduce. The first generate maps based on the given user's definition function, and the second groups of maps outputs together to computing answer. The very first useful when dealing with the batch of programs were data in manipulating in a sequential way. Recently, the map reduce attracted attention because of its applicability parallel computing. Google's MapReduce composed initially the GFS distributed file system, and the implementation of MapReduce brought to the fore use of the simple and consolidated functions map and reduce in parallel and distributed computing using Java and C++ libraries. This approach feeds the reduce function for the map function results. This enables parallelism since partially proportional to the data may be fed into the different instances of map tasks throughout the clusters. The results are then gathered using the outputs of the reduced instance. Based on the novel approaches, Dow Cutting, an employee of Yahoo at the time, and Mike Cafferel, a professor of the University of Michigan, developed Hadoop, later called as Apache Hadoop Framework. This is basically a brief history of the Hadoop, and the logo of the Hadoop is an elephant, which is something kept by the Dow Cutting simply by looking him toy of in his child's hands. One of the objectives of the semantic literature review is to propose a taxonomy and classify the related research literature into categories. Our taxonomy creation methodology was based on the project structure proposed by the Apache Hadoop developers. After careful review of the selected papers, we developed our proposed taxonomy, in which we classify our studies into four major categories related around Hadoop framework architecture. And the four major categories related to the Hadoop framework architecture are MapReduce, storage, ecosystem, and miscellaneous. The first category, MapReduce, includes studies and the development with solution involving the paradigm and its associated concepts, like scheduling, data flow, and the resources allocation. Data storage and manipulation categories include the studies comparing HDFS, gathering the studies involving the storage, replication, indexing, random access, queries, and something like cloud computing and storage, cloud storage, and something. Third category includes containing new approaches of the Hadoop ecosystem, including the papers related both existing and new components created to cope of specific classes and problems. Finally, the last category received the studies that did not fit well in the three categories, including the research involving GPU cluster energy management. And here is the taxonomy hierarchical organization of Apache Hadoop. The Apache Hadoop is further classified into MapReduce, data storage and manipulation, ecosystem, and miscellaneous. Under the MapReduce, we get the scheduling, data flow, and resource allocation. Under the data storage, the storage and replication, cloud storage, cloud computing, indexing, random access, DBMS, and queries, all the data related. And coming to the ecosystem division, we have the HBase and new components regarding the ecosystem. Under the miscellaneous, these are the category which does not belong to all three the previous term, the energy management, GPU, and data security and crypto. Scheduling, alongside with storage, is one of the most critical aspects of highly concurrent parallel systems and was the topic addressed by a large number of studies we analyzed. Originally, Hadoop comes with three schedulers: FIFO, FAIR, and capacity. The default Hadoop scheduler is the FIFO, where jobs are loaded into a queue, scheduled into, and executed according to the order in the queue. The FAIR scheduler was originally developed by Facebook and was later released by the Hadoop community. It gives a fair share of cluster capacity over time, thus its name. Jobs are put into allocated pools which receive a guaranteed minimum number of map and reduce slots. Using preemption, the scheduler manages the cluster to assure a fair share of resources to each job. The third scheduler, named Capacity Scheduler, was developed by Yahoo to guarantee a fair allocation of computational resources to a large number of cluster users. To do so, it uses queues with a configurable number of tasks slots. Resources are shared among the queues according to the priority. Free resources from the empty queues are temporarily allocated to the other queues. While the FIFO was the first and most simple scheduler implemented, the FAIR and the capacity schedulers were created to address the problems of managing multiple users sharing the same resources. We now present schedulers and new approaches designed to enhance the performance to solve untreated classes of problems in Hadoop. The data processing strategy employed by MapReduce consists of two primary functions: map and reduce. Behind this simple abstraction is a single fixed data flow. MapReduce job is divided into map and reduce tasks and assigned to idle slots of workers according to these two stages. Thus, there are two types of workers: mappers and map tasks, and the reducers to reduce tasks. In the beginning of the map phase, the input data is loaded into HDFS. To ensure fault tolerance, the input data are partitioned into equal sized blocks and replicated accordingly to replication factor. Each block will be processed by a mapper, resulting in intermediate outputs, which are locally stored, optimally combined from key value pairs sharing the same key. The store in local disk of the mappers. The reduce phase starts as soon as there is enough map outputs to start reduced tasks. In this moment, the scheduler assigns reduced tasks to workers. The data transfer is performed by each reducer that pulls the shuffles intermediate results using a one-to-one shuffling strategy. Reducers are responsible to read intermediate results and merge them to group all values with the same key. Subsequently, each reducer applies reduce to the immediate value considering these keys to produce the final output that is stored in the HDF. Storage and replication. The Hadoop distributed file system is the block storage layer that Hadoop uses to keep its files. HDFS was designed to hold very large datasets reliable using data replication. This allows HDFS to stream large amounts of data to users' application in reasonable time. Its architecture is composed of two main entries, name nodes and data nodes, which work in a master-slave fashion. Name node is reasonable for keeping the metadata about where the file is stored in the file system. The data nodes are responsible for storing the data itself. HDFS works as a single writer, multiple reader file system. When a client opens a file for writing, it is guaranteed a lease for the file and no other client can write on the file until the operation is complete. Additionally, after the file is closed, the bytes written cannot be altered or removed except the new data can be added to the file by reopening the file for append. HDFS has received several contributions that implements enhancement so that it can be used in different type of approaches in MapReduce computations. Cloud computing. Although designed to be applied to on distributed environments, Hadoop was not originally conceived to work using cloud computing concepts. In this sense, some approaches try to cope with these needs. Regarding cloud computing management, some of them design a data management system to enable storage as a service transparently using Hadoop. It is a service that is transparently using the Hadoop. To do so, some of them developed a new file system ODFS, Optimist Data Manager and Distributed File System. Using HDFS as a base, the file system adds RESTful interface to expose critical functionalities from Hadoop as a service and extends HDFS. These components are used to enrich security, logging, and data analysis features. Components also provide data access compatibility between federated clouds. The main contribution resides in the fact that ODFS enables suitable interface with the external infrastructure provided to launch storage VMs and extend the distributed file system, creating a transparent cloud federation to the user. The design and implemented network-aware scheduler to be used on federated clusters, improving the map task scheduling in such environment and consequently achieving better performance. In 2013, Wang has proposed G-Hadoop and MapReduce framework that enables large-scale distributed computing across multiple clusters. It replaces HFDS from the G-Farm file system and schedules tasks across the multiple nodes of multiple clusters controlled by different organizations. To provide a Byzantine fault tolerance into Hadoop, later in 2009 proposed Upright Zookeeper and Upright HDFS using the Zookeeper and HDFS open source code bases. Zookeeper was modified, adding authenticators to message and to send, receive them, and to from write columns of nodes. These modifications allow Zookeeper to protect the clusters against a wide range of faults. Data transfer between the nodes in the cloud computing environment may consume larger bandwidth with time. The use of such resources represents an evolution to cost to the user. An approach to solve these problems, Hadoop rsync, is presented by in 2011. Such approach uses an incremental update driver from the original rsync, which minimizes the data transfer. All the HDFS shows good performance on scalability, fault tolerance, high throughput, and flexibility to handle unstructured data. It presents drawbacks in some contexts where compared with the database management system (DBMS) and other approaches. Several studies intend to improve Hadoop's performance, altering or replacing HDFS with other solutions as presented before. Some approaches intend to develop indexing, query processing, hybrid solutions using DBMS and structured data processing inside the Hadoop. Further, most studies present advanced solutions comprising more than one of these strategies as follows. Leo and Durich in 2012 proposed improved Hadoop's performance by means of complete new indexing manner. Later in 2010, they suggested alter existing indexing mechanisms as their strategy. Leo in 2010 proposed the use built-in hierarchy indexing to support complex types of queries in HDFS. In 2012, they also proposed an enhancement of HDFS and Hadoop MapReduce that improves runtimes and several classes of MapReduce jobs. Coming to the Hadoop ecosystem, the MapReduce is not suitable for all problems involving the large datasets. The four modules that concurrently compose the Apache Hadoop Core, Hadoop Common, HDFS, MapReduce, and YARN are well suitable for unstructured data. However, when processing common old-fashioned structured data, Hadoop may suffer from performance issue since the framework was not originally developed to process these data. To overcome these problems, several Hadoop-related projects have been developed over the past years. For example, PIG, a high-level data flow language and execution framework for parallel computation. Manohar, a scalable machine learning and data mining library. Hive, a data warehouse infrastructure that provides data summarization and the Hawk query. And the HBase, a scalable distributed database inspired on Google Big Table that supports structured data storage for large tables. Energy management. The reduction in cost of hardware enabled corporations to increase the number of data centers and machines. Consequently, energy consumption has become a vital issue regarding the cost of data storing and its processing. Regarding the Apache Hadoop clusters, Lee in 2011 proposed an algorithm for maximizing throughput of a rack of machines running a MapReduce workload. Subject to the total power budget, the main idea is to optimize the trade-off between job completion time and the power consumed. The novelty is the approach relies on the accounting for thermally induced variations in machine power consumption. The algorithm minimizes job completion time for any given power budget. Later, the Green Hadoop proposed by Gori is an Apache Hadoop variant for data centers powered by photovoltaic solar arrays and electric grid as a backup. The objective is to investigate how to manage the computational workload to match the green energy supply in small medium data centers running data processing frameworks. However, scheduling the energy consumption of MapReduce jobs is challenging because they do not specify the number of servers to use, their runtimes, or their energy needs. Moreover, power managing servers should guarantee that data to be accessed by the jobs remaining available. Green Hadoop seeks to maximize the green energy consumption of the MapReduce workload or equivalently minimize the brown energy consumption. GPGPU, General Purpose Computing on Graphical Processing Units, is a technique to use commodity GPUs to perform general purpose computing in application traditionally handling by CPUs. CUDA and OpenCL are examples of integrated development environments that may be used to such purposes. The hybrid map task scheduling technique for GPU-based heterogeneous computer clusters is introduced in 2010. The developed job schedulers assign the map task onto CPU's cores and GPU devices in order to minimize the overall MapReduce job execution time. The schedulers use profiles collected from dynamic monitors of map task behavior to decide where to schedule a task. Jobs contains tasks that have data parallelism may be suitable for GPU execution, while tasks containing many branches of synchronization are not recommended to be executing approach using this approach. The model uses Hadoop pipes and C++ interface to Hadoop MapReduce. Hadoop pipes uses sockets as channels over the task trackers communicates with the process running the C++ based map and reduce functions. It uses justified because other native methods such as Hadoop streaming and Java native interface may introduce significant overhead representing loss of performance. Data security and cryptography. In the cloud computing era, data security, privacy, and integrity became most important features to be supported by frameworks and service providers. In Apache Hadoop, data is stored according to the user accounts. This mechanism may not be secure enough when dealing with data spread across multiple data center and cloud providers. Some studies addresses these problems, presenting solutions to enhance both Hadoop data security and confidentiality. In 2009, we designed a model that enhances the basic MapReduce framework with a set of security components. In open systems, MapReduce faces a data processing service integrity problem. Since service providers may come from different administration domains, they do not always trustworthy. The approach is meant to provide a service integrity assurance framework for MapReduce, applicating some tasks and assigning them to different mappers and reducers. This is achieved by using a differential replication based integrity verification scheme for running MapReduce in open system. It uses a set of security properties such as non-repudiant and residential DOS attacks and reply attacks while maintaining the data processing efficiency of MapReduce. Now let us discuss about the Hadoop evolution. Since this initial release, Hadoop changed consequently and considerably in 59 releases. The latest version is 2.2.0 on October 15, 2013. Over 6 years of development, besides bug fixes present is in each one of these releases, new features and modules were developed and incorporated, consolidating a framework as the main solution to process large amounts of data using the MapReduce paradigm. Some releases deserve special attention. For the initial releases, versions 0.2.0.x were the first one considered most stable, which could be used on production environments. The first one is released in 2009 April, and this branch was one of the longest achieved branches in the history of the Hadoop. This release missed an important features present on the subsequent releases. Support for the files appending on HDFS. A couple of years later, version 0.23.10 was released. Being considered alpha quality releases, they included two important features to the present Hadoop version: HDFS Federation, and the initial release of the Hadoop Next Gen MapReduce is known as the YAM. In 2011, after years of development, Hadoop reached 1.0 version. This release includes web HDFS and security features on HBase. Besides performance enhancements being a cut from the 0.2.10 branch, it now includes bugs, fixes, and features incorporated in 0.2.010. This was fixed later in 1.10 releases. On May 2012, Hadoop 2.0 was first released. This includes the significant major feature over the 1.x series derived from 0.2.3x branch. Theoretically, although still supported in versions 2.10, the distance between the version 1.10 extends to increase in the future. Backwards compatibility in version 2.10 will no longer be supported. This is reasonable since the separation between the resources management and the job tasks allocated benefits the cluster infrastructure in terms of users and flexibility. As shown, we have been identified several infrastructure studies that involve over the last 5 years using the Apache Hadoop and its ecosystems.